In Chapter 7, we're talking about the quantum mechanical model of the atom. So we have to talk about quantum mechanics. Until the beginning of the 20th century, it was believed that all physical phenomena followed the same rules that visible objects do. This is called Newtonian physics. We know that if you throw a baseball, you can calculate where it's going to go. Where it is now and its velocity predicts where it's going to go in the future. We had no reason to think otherwise. But there were many famous physicists at that time that discovered almost simultaneously that for subatomic particles, those rules just don't apply. The present condition does not necessarily determine the future condition. If you were able to shoot an electron like you would throw a baseball, and you measure where it went, where it landed, and you take another identical electron and throw it in exactly the same way, it would probably land somewhere else. This doesn't make sense in terms of things that we can see. So the absolutely small, which an electron falls into that category, another word for the absolutely small is quantum. This world behaves differently than the large world that we can see, large or macroscopic. What's really hard to understand about this quantum world is that these absolutely small particles like electrons, if we are not looking at them, can be in two states at the same time. You might even argue that they could be in two places at the same time. An example of this is a radioactive nucleus. This is on the level of the absolutely small. Can be simultaneously emitting a particle or not emitting a particle. But when you observe it, it has to be one or the other. When you're not observing it, it can be both and neither at the same time. And if it's hard to get your mind around that, then you're listening. Because even Einstein couldn't figure out, he couldn't get his mind around this. It's very, very mind-blowing. We have to understand that electrons are incredibly small. I mean, atoms are incredibly small. Electrons are 2,000 times smaller than the proton in the nucleus of the atom. So they're just, we just can't even understand how small they are. A single speck of dust has more electrons in it than the number of people who have ever lived on the Earth. That's a lot of electrons. And they're not even packed tightly together. There's lots of empty space between them. You could fit more in there if you get them all together. And what we have to understand is that the electron behavior determines a lot of the behavior of the atom. And so that's why it's important to look at what do these electrons do. We cannot directly observe electrons in an atom. Even with scanning tunneling electron microscopy, we can barely get an image of relatively large atoms. There's no way we can see an electron, and because it is so small, observing it changes its behavior. So if we can look at it, then we're not observing what it is. It's a little bit like that kid that was in your class in school, right? And when the teacher was around, he was really nice. But as soon as the teacher or the playground supervisor turned their back, he was picking on people. But nobody could ever catch him because when a grown-up observed him, his behavior changed. That's a little bit, tiny bit what electrons are like. Even shining a light on an electron, you're not looking at it. Even shining a light on it changes its behavior. It's hard to understand. So I'm going to show you two videos about a thought experiment involving what's known as Schrodinger's cat. It's important to understand that no cats were harmed in any of these experiments because the experiment was never done. We just think about it. And the point of this thought experiment is that the strangeness of the behavior of the quantum world, or the absolutely small, does not translate to the larger world. It doesn't make sense. So let's see if I can get this to work. Okay, so we just watched these two videos, and if you're watching on YouTube, I put these two videos in the playlist. And so my students here, if you want to watch them again, they're in the playlist on YouTube. So this idea of things being two different things at the same time should bother you. And it bothered the scientists that were working on this. Niels Bohr was involved in this, and he said, anyone who is not shocked by quantum mechanics has not understood it. Schrödinger, who came up with this thought experiment about the cat, wrote about quantum mechanics, I don't like it, and I'm sorry I ever had anything to do with it. These are elite scientists. And Albert Einstein, you've heard of him. He didn't like it either. He attempted unsuccessfully to disprove quantum mechanics. For the rest of his life, he tried. He couldn't disprove it, which kind of suggests that maybe it's true. But he didn't like it either. It's hard to understand. This quantum mechanical model, though, explains how electrons behave and exist in atoms. It helps us to understand the properties of atoms related directly to the behavior of the electrons. Things like why some elements are metals and others are nonmetals. Why is oxygen a nonmetal? Why is iron a metal? Quantum mechanics can help us to understand that. Why do some elements gain an electron when forming an anion, gain one, and others gain two? Why? Some of you may have wondered it. It's not just because, oh, they're in that position on the periodic table. There's an explanation behind it. It's not maybe an explanation you are going to like, but it's there. Why are some elements very reactive, like sodium? Others are practically inert, like the noble gases. And it also explains other periodic patterns that we see in the elements.